Okay, let me welcome all of you to the last review session in organic chemistry for the spring 2014 semester. In today's session, we are going to review for the fourth exam, that is exam number 4, that is scheduled for Thursday, April 24, and that is also the last day of class for the spring 2014 semester. Okay, I noticed that some of you have joined us, so I will recognize you as during the course of this session today. But what I want to do now, I want to use the spring 2013 exam 4 for today's review session. And I know that some of the questions in this exam we have done in class. So for today's session, what I will do is we are going to now work on problems 3, 4, 6, 7, 9, 10, 14, and 15. I hope all of you guys have a copy of that exam with you. Okay, so to get the session started, what I want to do, I want to start with question number 9. And I know many of you are very comfortable with reactions and reagents. So therefore, let us start with question number 9. And this will be sort of like an icebreaker to get the session started. Okay, to do this, let me call on Rua. Can you read this question for us?
Provide the missing reagents in the following synthetic scheme.
Okay, very good, but don't go yet, don't go yet. Just turn on your mic again.
Okay.
Okay, I need your help in doing some of these problems here.
Okay.
Okay, now what do we need to do for this here, for the first sequence?
You would
going from benzene to methyl to toluene.
Friedel-Crafts alkylation.
Okay, Friedel-Crafts alkylation. Excellent, excellent. So you want us to do Friedel-Crafts alkylation. Okay, I'm assuming that you want us to use here. You want us to use methyl bromide.
Yes.
Or methyl chloride. Is that correct? Okay. In the presence of aluminum chloride. Okay, very good. That is good. Excellent. How about step 2? Now we want to go from toluene to nitrotoluene. What reagent do we need here?
Nitration, you do HNO3 with H2SO4.
Okay, excellent, excellent. So you want us to do a nitration? That is good. And for this, the reagent you need for this is nitric acid in the presence of sulfuric acid. Is that correct? Okay, very good. Now let us, one more before you go. Okay, help me out with number 3 right here. Now we want to go from the nitro to the amino.
You would do tallolic hydration, H2 over PP. Okay,
very good. In other words, you want us to do hydrogenation, to do a reduction here. So you want us to use hydrogen in the presence of a catalyst. It could be palladium or it could be platinum. That is excellent. For this transformation also, going from a nitro to an amino, you could also use iron in dilute acid. Okay. Also, you could also use for the transformation of the nitro to the amino group, you could also use lithium aluminum hydride followed by dilute acid. or I would say or lithium aluminum hydride, step 1, and then you follow that up with dilute acid or sometimes just with water. Okay, so all of these 3 reagents here will allow us to go from a nitro to the amino. So this is another example of a method for making amines. Okay, so Rua, thank you very much. If you could turn your mic off now. Okay, now number 4. Okay, in number 4, we now have to go from an amino group to this group right here. We call this the diazonium ion. In order to do this, I am going to take a little time off from this particular slide and give you a little bit of background. Okay, and so I'll give you a little bit of a mini lecture here. So just bear with me for a minute. So I am going to call this diazotization of amines. Diazotization simply means formation of diazonium ions. Now, what does that mean? If you have this molecule here, does anybody know the name of this molecule? Can you give me the name of this molecule? Just send me the name through the text window. Or you could pick up the mic. Oh, aniline. Excellent, aniline. Okay, by the way, Alexis, you are welcome. I also see Camille Iman, Mashake Hutchinson, and Didi Njoku, Rua Afid. You are all welcome. Okay, so if you take aniline, and you take this molecule here, nitrous. This is a very important reaction. So make a note of this. Take nitrous acid. Notice this is not nitric acid. This is nitrous acid. In the presence of sulfuric acid. So if you take this reagent here, what it will do is to convert the amino group to a nitronium ion. This is a very, very important reaction indeed, so you need to make a note of this. To a nitronium ion. Okay, of course, to balance the nitronium ion, you have here a counter ion. In this case, hydrogen sulfate. Now, so we call this a nitronium ion. Now, very often, this nitronium ion will simply just write it this way. Okay, very often that is the way we write it. Okay, so we may not write it this way. Okay, now the question is, what can we do with the nitronium ion? If you have the nitronium ion, you could react the nitronium ion with this reagent here, hydrogen bromide, in the presence of copper 1 bromide. And what does that do? You will replace the nitronium ion with bromine. So this sequence here allows us to introduce a bromine atom on the benzene molecule. In other words, you go from the amino group, react with this reagent here, nitrous acid in the presence of sulfuric acid, to get nitronium ion. Then you add hydrogen bromide in the presence of copper 1 bromide to the nitronium ion. You replace the nitronium ion with bromine. Now, supposing we want to replace with iodine, then you use this reagent here, sodium iodide. You get this here. So this is a very important reagent indeed. Supposing we want to replace with cyanide, we take the nitronium ion, we take potassium cyanide in the presence of copper 1 cyanide. So this reagent here, okay, what that does is to replace the nitronium ion with a nitride. So you begin to see the importance of the diazonium reaction here. Now you guys already know what you can do with each one of these products here. You could also take the diazonium ion, react with copper 1 oxide in the presence of copper 1 nitrate. Okay, so this reagent here what this reagent here will do is to replace the diazonium ion with hydroxide. Now that is not the end of it. Okay, let me take this out of the way. Now we could also take the diazonium ion, react with this molecule here, called hypophosphorus acid, this here, and then what does it do? We replace the diazonium ion with hydrogen. Many of you will say, why would you want to do that? Okay, we'll get to that in a minute. Okay? So these are all these reactions of the diazonium ion. Okay, we could use the diazonium ion to go to each one of these different types of molecules. Now, each one of these reactions that I've just given you, we refer to all of these as Sand-Meyer reactions. Take this out of the way. All of these here we refer to as Sand-Meyer reactions. In other words, for the Sandmeyer reaction, once you have your diazonium ion, you could then react the diazonium ion with any one of these reagents here to give the appropriate product. Okay? Now, how do we use this diazonium ion? Supposing I ask you to go from here from benzene. I want you to go from benzene, and I want you to make this molecule for me. Just to give you one example of how you could use the diazonium reaction. And other examples will follow when we get to the rest of the problems. Supposing I want you to make this molecule for me. Now, each one of you by now will know that the bromine on a benzene molecule is an auto para director. So there is no way we could make this molecule ordinarily, because each one of these bromine here is an auto para director. However, the good news is, if you take aniline, aniline is so reactive, it is an auto para director, that if you take bromine, or in the presence of water, because this aniline is so reactive, the amino group is an activator. In other words, it pumps electron into the ring system by resonance, because you have non-bonding pair of electrons here. This is what you will get. You cannot stop this reaction by simply doing monobromination. All of the possible products at the position will react. In other words, you are going to replace hydrogen here, and hydrogen here with bromine. So this is what you will get. Now, this is where the diazonium reaction comes in. Keep in mind, this is what I want to make. I could now do my diazonium reaction, nitrous acid. Keep in mind, for the diazonium reaction, you need nitrous acid, not nitric acid. Keep that in mind. Nitrous, not nitric, because you do not want to lose any point here. Nitric acid is this, and nitrous acid is this, NO2, okay? Now, so now I take this in the presence of sulfuric acid. I get my diazonium ion. Now, I want to remove the diazonium ion, since I want to come here. What do? I now use the hypophosphorus acid. So that will answer the question, why would you want to replace the diazonium ion with an hydrogen? Because that is what we've done here. Okay? Now, if you follow that, give me a happy face. If you follow what I've given you so far, give me, okay, very good. Now let us go back to question number 9. Okay, question number 9. Now we now need to continue with question number 9. We'll get this out of the way. Okay, therefore. So what is the reagent we need to go from this amino group to the diazonium ion? Can you guys give me the reagent now? Very good. Nitrous acid in the presence of sulfuric acid. Very good. So now the reagent here is nitrous acid in the presence of sulfuric acid. That is the reagent you need for diazotization. Okay, keep that in mind. That is a very important reaction. Okay, now we have now formed our diazonium ion. Now we want to replace the diazonium ion with hydroxy group. We want to form a phenol. What reagent do I need here for 5? What reagent do I need here? We are replacing the diazonium ion with an OH group. Okay, copper oxide. Excellent. So now we have to use copper 1 oxide in the presence of copper nitrate, copper 1 nitrate. Okay, very good. So that is what we need for here. About number 6. Now we want to go from here. We now want to form this benzyl bromide. This is P-hydroxy benzyl bromide. Let me take this out. Okay, so what reagent do I need here? Okay, keep in mind, what are we doing? We are replacing an hydrogen on this carbon here with a bromine. What reagent do I need? MBS, exactly. Folks, please do not forget all of your reagents. You need to remember all those reagents. Without knowing your reagents, you cannot do anything in organic chemistry. So here you need NBS. What NBS will do, generally in the presence of light, is to replace a benzylic hydrogen. When we say benzylic hydrogen, that would be, if you have benzene, attached to a carbon atom, and that carbon atom is attached to hydrogen, this carbon here, this is what we call a benzylic carbon, and therefore this hydrogen here is a benzylic hydrogen. And generally, therefore, we refer to this group here as a benzyl. Okay, we refer to this as a benzyl group. Okay, just as you have a methyl group. Okay, we also call this a benzyl group. Okay, therefore, to replace the benzylic hydrogen, we use MBS in the presence of light. Okay, about number 8. We want to go from the cyano group to an amine, a primary amine. What do you need here? What do we need? We want to go from a cyano group to a primary amine. What do we need? What reagent do we need? LAH. Excellent. Folks, I keep telling you, do not forget your reagent. You need to know those reagents. Okay? So here, step 1, lithium aluminum hydride, and then you follow that up with either water or dilute acid. Okay? And what this does is to take a nitride and replace transform the nitride to an amino group. If you notice here, the carbon of the nitride becomes a CH2, a methylene group, and of course the nitrogen becomes your amino group right here. Okay. Now, if this is all clear to you, question number 9, give me a happy face. Okay, very good, very good. Okay, now let us go to the next one. What I want to do now, I will go back to question number 3. Okay, Mashake, if your mic is working, can you go ahead and read this question for us?
Provide names for 5 of the following compounds.
Okay, thank you. In this case, I want you to provide names for all of the compounds below. Okay, let us take a look at the first one. What is the name of this compound here? What is the name of this compound? Okay, I need your help here. Given the fact that this molecule here is called aniline. Okay, so what is the name? Okay, 2,4-dibromo-benzamine. Okay, very good. But I do want you to use the aniline word, yes. The aniline is what I prefer for you to use, but that is fine. Actually, it should be phenyl. It should be, yeah, okay, I see. Okay, but yes, the aniline name is what I prefer, but all of you are correct. It's 2,4-dibromoaniline. 2,4-dibromoaniline, very good. Okay, so this is 2,4-dibromoaniline. Okay, very good. How about B? How about B? Okay, to name this. Okay, I will give you a little hint here. The base name for this is this here. Okay, so therefore, and this cyclo or pentyl group will be a substituent for that base name. Okay, somebody say cyclopentyl. Very good. 2-cyclopentyl ethanamine. That is good. We could do that. Okay. So say 2-cyclopentyl ethane. Okay. If you use the corresponding alkane name, then you remove the E ending. And then the attach amine. I'm sorry. Amine. Very good. In other words, this is position 1 and this is position 2. Now you could also name this as 2-cyclopentyl ethyl. Use the alkyl name ethyl amine. Okay, that is also acceptable. In other words, just give the alkyl name of the alkyl group. Okay, that will then attach to the nitrogen. That will become your base name. In this case, the cyclopentyl group is still in the 2 position. Okay. About this one here. About C. Okay, about C. Okay. The hint on this? Okay, N-ethyl cyclo, exactly, very good. N-ethyl cyclopentanamine, okay. Okay, you guys are right. N-ethyl cyclopentylamine, that is also correct. Very good. Okay, so therefore, let us give the name. So this becomes N-ethyl cyclopentylamine, because this here becomes the base name, because the cyclo-ethyl group is more complex than the ethyl group. So that becomes the base name. I'm sorry, this part here becomes the base name. You could also name this as N-ethyl cyclopentane. Then remove the E ending, then you add amine, cyclopentamine. Okay? So that is also possible. Okay, this one is this one here. Okay, so let me erase this to remove, give ourselves some space. How about this one here? D. What is the name for D? Okay, I need your assistance here. Okay, what is the name for D? I hint the base name will be due to the more complex alkyl. Okay, that's N-dimethyl cyclopentylamine. Excellent, excellent, excellent. So this becomes N, N N-dimethyl, because you have two methyl group attached to nitrogen. So you say N-dimethyl. Then you give the base name, cyclopentylamine. Or you could use this here, or N-dimethyl cyclopentanamine. Okay, both of those will be acceptable. Okay, finally, let me now give you this one here. Take this out of the way. For this here, okay, let me give you a little bit of a background for that. Okay, Frederick, Todd, you are welcome. I noticed that you joined us. Also, Alexis, Thibault, you are also welcome. Okay, now for this molecule here, E, let me give you some background to that. If you have this here, this molecule here, we call this molecule pyrrole. Okay, it is an aromatic molecule. If you recall when we did, I believe this was in chapter 15 or 16, we did aromatic molecules. So this would be an aromatic molecule. One of those molecules referred to as heterocycle. Okay, in other words, this is a cyclic molecule that contains other atoms other than carbon. Most of the cyclic molecules we deal with contain carbon. On the other hand, in the case of the heterocycle, they contain other atoms like nitrogen and oxygen. Okay. Anyway, this is called pyrrole. And this one here, okay, if we completely hydrogenate this pyrrole here, this becomes pyrrolidine. This becomes pyrrolidine, okay? Okay, so I've been giving you that information. What are you going to call this? The base name will be pyrrolidine. So what will be the name of this here? E. What will be the name for E? What will be the name for E? Anybody has an idea? N-propylpyrrolidine. Excellent. Oh, very good. Excellent. That is exactly what I want to say. So this therefore becomes N-propylpyrrolidine. Okay? Because the propyl group is attached to the nitrogen of pyrrolidine. Okay, very good. Now let us go to question number 4. Now we want to get into synthesis. Okay, Alexis, is your mic working? If it is working, can you read this question for us? Okay, probably not. Okay. Victoria, if your mic is working, can you read this question for us? Oh, okay, your mic is not working. Okay, let me go back to Arua. Can you read this question for us? Okay. Okay, but Mashake, is your mic working? Can you read this for us?
Provide a synthetic scheme for NN-dimethylbenzylamine on toluene.
Okay, very good, and thank you. In other words, what do they want us to do here? They want us to go from toluene. This molecule here is called toluene. Okay, that's the toluene. And they want you to go from toluene to this here. N,N-dimethylbenzylamine. In other words, they are also testing your knowledge of nomenclature. Okay, so benzylamine will be this here. Remember, we gave you what the benzyl group is earlier. This will be benzylamine. Don't forget that this group here, this here is your benzyl group, right here. So when we say benzylamine, this is what we mean. Now, it also says N,N-dimethylbenzylamine. So that means we take off these two hydrogen here. N,N-dimethyl, in other words, two methyl group attached to this here. Okay, so this is what they want us to make. They want us to go from toluene to N,N-dimethylbenzylamine. Give a synthetic scheme. Okay, let us do a little bit of analysis here. What do we want to make? Apparently, we need to attach to this carbon, we need to attach a nitrogen atom. Okay, in this particular instance, we also need to make a tertiary amine. So this is one of those instances in which you need to know how do we make a tertiary amine. Okay, is there any body can help us with this? Okay. Okay, excellent. From carboxylic acid. MBA, okay, excellent, excellent, excellent. Okay, you guys are rolling tonight. Okay, from carboxylic acid. And then you say before we do that, we need to do the MBS, presence of light. Of course, that will give us benzyl bromide. Okay, now to form the carboxylic acid, what do I need to do to form the carboxylic acid? I do a Grignard, right? Step 1. And then I add to the Grignard carbon dioxide. And then after that, hydronium ion. Oh, no, I'm sorry. Jumping my... No, let me take that back. Let me take that back. Okay, I was thinking of another problem. Let me take this one back. You guys were right. No, we do not need to do MBS here. Okay. The person who say carboxylic acid, that is correct. To form the carboxylic acid, potassium permanganate in the presence of dilute acid. So you form your carboxylic acid. So you are right to form carboxylic acid. Now, once you form the carboxylic acid, what do you do with it? This is where we want to go. Right here. What do we do with it? Okay, very good. Excellent. Excellent. So, okay, we now do you form, take the secondary amine. Take this secondary amine. Since we want to form this part of the molecule right here, right? Okay, in the presence of DCC, that will give us a tertiary amide. That will give us a tertiary amide. And then what do I do with this tertiary amide here? What do I do with the LAH? Exactly. Okay, so folks, once you know your reagents, you are in good shape. Okay, now you do lithium aluminum hydride, step 1, and then step 2, dilute acid or sometimes water. And that will take your tertiary amide to a tertiary amine. Notice what the LAH will do here is to transform the carbonyl of an amide to a CH2. Okay. Now somebody said that I missed one question I missed one of the questions in 3. Let me go back here. See, we did not do F. Oh, okay. Yeah, we did not do F. Let me go back to this. Okay, thank you for pointing this out to me. I think I just overlooked that. Okay, so let us do here F. Okay, in the case of F, since you have another functional group here, which is a nitrile, then the amine group has got to become a substituent. Okay, and this is an amino group. Okay, so if we are going to name this as a nitrile, this will be carbon 1, carbon 2, 3, 4. Okay, so what will be the name of this here? What would be the name? 4-aminobutane nitride. Excellent. 4-aminobutane nitride. One word. Okay, so now we have completed number 3. So now let us go to 6. Okay. If your mic is working and you have not spoken tonight, can you go ahead and read this for us?
Starting from butanoic acid, show how you will synthesize propylamine via the Hofmann reagent. Only structural synthetic scheme is required.
Okay, very good. And that is Frederick Todd. You are welcome. Okay. So they want us to start with butanoic acid. Butanoic acid. And then you have to make propylamine. And of course, they have given you a clue here, or a hint. You want to use the Hofmann rearrangement. Okay, so we start off. Okay, start with butanoic acid, which is this here. And then they want you to go to here. Actually, by giving you a hint, they have made this problem very easy for you. Because if you notice here, we are losing a carbon atom. Because you are starting with 4 carbon intermediate. And you are ending up with a 3 carbon product. I'm sorry, a 4 carbon starting material. And you are ending up with a 3 carbon product. Okay, of course, you know that to do that, to lose a carbon atom, the chances are you have to do an Hofmann rearrangement. So what do we do here? Okay, what do we need to do? We need the synthetic scheme. What is the first thing that we do? Okay, let's see. Okay, this is it. Okay, ammonia. Okay, very good. Okay, so we say ammonia with DCC. Very good. So you want to form an amide, a primary amide. Now then, what do you do with that? Then what reagent do you now need to get to the product? This is a very simple one. Okay, excellent, very good. So now you now go straight to here by using hydroxide, okay, in water in the presence of bromine. And that is your Hofmann rearrangement. Okay, very good. Okay, so if this is clear to you, give me a happy face. That is a very simple one. Okay, very good. Now let us go to 7. Okay, Rua, if your mic is still working, can you read this for us?
Starting from toluene, methylbenzene, provide a synthetic scheme for p-hydroxyphenolacetic acid.
Okay, thank you. Okay, for this problem here, this is a lot more involved than the last problem. So what do they want us to do here? They want us to start with toluene. And then they want you to make, in other words, you start with toluene, and then they want you to make p-hydroxyphenylacetic acid. phenyl acetic acid. Okay, this is acetic acid. Okay. Okay, this is a phenyl and this is acetic acid. Okay, so they say p-hydroxy phenyl acetic acid. Okay, so this is what they wanted to make. Okay, a little bit of analysis here. Okay, as you can see here, we need to introduce an hydroxyl in the para position, para to this methyl group. And then also, we need to make a new carbon-carbon bond in order for us to join this carbon here to this carbon to form a carboxylic acid. So what do you want to do here? What is your strategic plan for making this particular molecule from toluene to this here? Anybody has an idea? What do we do first? Anybody has an idea? What do we do? Okay, nitration. Okay, very good. Very good. I think I know where you want to go here. Nitration. Then use diazonium ion. Excellent. 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 In other words, so you want us to start with to do nitration. Do not forget nitration now, which is nitric acid in the presence of sulfuric acid. The methyl group is an auto-para director, so we are going to direct to the para position, since that is the product that we need. Now, once you do that, then what I will advise you to do at this point, before you make the hydroxy group, because I think I have an idea where you guys want to go here. You want to form a diazonium ion and then introduce the hydroxy group. Okay? And then, of course, you want to form a carbon-carbon bond. Okay, I see somebody say they are using a Grignard reagent. Keep in mind, you cannot do a Grignard in the presence of hydroxy. So therefore, let us do the Grignard first before we transform the nitro to the hydroxy. Okay? So I will say we do MBS. This is the reaction I was thinking of earlier. And then you get this. And of course, the nitro is still here. And now you then do your Grignard. Step 1, magnesium. Step 2, you dump in some carbon dioxide, which is dry ice. And then step 3, you add the hydronium ion, and then you get your phenyl acetic acid. This time it will be p-nitro phenyl acetic acid. Now, what do you want to do with this now? With the p-nitro phenyl acetic acid. Okay, you want to now form diazonium. Okay, very good. But to form diazonium, what do you do first? Okay, very good. You convert to amino. Okay, you guys say you want to use iron. Okay. In this case, you do not want to use a lithium aluminum hydride. Why not? Why don't you want to use lithium aluminum hydride here? Does anybody know why? Because that will react with the carboxylic acid. Excellent, excellent. Those are the kind of critical thinking I do expect of you guys. Okay, so now you have this. Let me make this a little shorter. Now you have this. Okay, now you formed your amino phenylacetic acid. And now once you form your amino phenylacetic acid, now you can now do your diazonium reaction. Step 1, nitrous acid. Keep in mind, this is nitrous acid, not nitric acid. That will give you your diazonium ion. Then step 2, copper 1 oxide in the presence of copper 1 nitrate. Okay, this reagent here will replace the diazonium ion with the hydroxy group. Okay, somebody asked a question for me. It will reduce the, yes, very good, very good. Okay, if this is clear to you, give me a happy face. Okay, so now we can move on. Okay, so now let us go to question 10. I think we are moving right along. Okay. Masha K, can you go ahead and read this for us?
Starting from p-bromotoluene, provide a synthetic scheme for benzyl bromide.
Okay, very good. Thank you. Okay, so what do they want you to do here? Starting from p-bromotoluene, provide a synthetic scheme for benzyl bromide. Okay, so this is what they want you to do. P-bromo, this is toluene right here, and then p-bromo. Okay, they want you to go to here, benzyl bromide. They want you to go to benzyl bromide. Now you see what is happening here. Apparently, we are going to have to lose the bromine. Somehow we have to lose the bromine. And then also somehow we need to replace one of the hydrogen on this methyl group with a bromine atom. Okay, I'm sure you guys know how to do that. But now the big question here is, how do you remove the bromine atom from benzene? Okay, so let us look at the synthetic scheme. I need your help here. What is the first thing you want to do? Okay, you want to do MBS? Okay, very good. Okay, so we want to do MBS. Let me start from here all over again. We want to do MBS. Okay, MBS. I'm assuming that you want to replace one of these hydrogen here, so you get this right here. So you get this right here, okay? Okay, so far so good. Now what do you want to do now? Oh, okay, magnesium. Okay, you want to form a carboxylic acid. I think I have an idea where you want to go here. Step 1, magnesium. Step 2, dry ice or carbon dioxide. Step 3, hydronium ion. So now you want to form a carboxylic acid. I think I have an idea where you want to go with this. So once you know your reagents, it's easy for you to actually think very clearly and get to where you want to go in terms of the synthetic designs. Now you form this. Okay, so now where do you want to go with this now? Okay, DCC, very good, very good. Ammonia with DCC. So now you want to form a primary amide. Excellent. Now you form a primary amide, then what do you do? Okay, Hoffman. Okay, very good. Now you want to do your Hoffman. Now you want to do Hoffman rearrangement. Hydroxide in the presence of bromine. And now that will give you the amino group attached to benzene. Of course, when you do that, you also lose carbon dioxide here. Okay, now what do you do at this point? Now, what do you do at this point? Okay, from the diazonium ion. Very good. Nitrous acid in the presence of sulfuric acid. And so that gives you your diazonium. Plus your diazonium ion. And then what do you do? Hypophosphorus acid. Excellent. 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 So you can see here, this question is not as innocent as it looks. It's a fairly complex question. That means you have to think critically. Okay, and that would, this reagent here will replace the diazonium ion with hydrogen, and then you get to your final product. Okay, and this product here, that is what they want us to make. Okay? Okay, now if you follow that, give me a happy face. Okay, very good. Okay, so we have 2 more questions to go, and then we'll call it a day, because it's after 9 o'clock already. Okay, let us go to question 14. Okay, this should be fairly easy. Okay, now if your mic is working and you have not spoken with you tonight, or you have not read a question for us, can you pick up the mic and read this question for us? Okay, that is it. Okay, let me, Frederick, go ahead and read this question for us.
Propose a structure for the amine having the following P-NMR spectrum. The multiplicity and number of hydrogens and signal are provided.
Okay, thank you. Now, this is a P-NMR spectrum, Proton-NMR spectrum. Okay, we are also told you that the multiplicity and the number of halogens will be provided. So, This peak here, this peak right here, this is a triplet. Of course, this one here, this is your reference TMS, so we don't need to worry about that. That is your reference signal from our TMS. This peak here is a singlet. This peak here, this peak right here, this is a quartet. Quartet. Okay. This peak here, doublet. And this peak here is a doublet. Now, in terms of the number of hydrogens, this peak here, this is your integration peak. Your integration line. These are your integration line. And those integration lines, what they give us is to give us the area, the ratio of the number of hydrogens that are responsible for those peaks. This one here and this one here. Okay, here is 3 hydrogen. Okay, we will give that to you. Very often, the instrument will determine that. Okay, this here is 2 hydrogen. This one here is another 2 hydrogen. This one here is 2 hydrogen. And this one here is another 2 hydrogen. Okay. Now, I know it's been a long time that we did our NMR spectroscopy, so I am going to help you out here. Anytime, of course, you see a signal somewhere between 6.8, anywhere around here, the chances are you are dealing with a benzene molecule. Okay? The chances are you are dealing with a benzene molecule. Okay, the hydrogens of benzene, that is where you expect the signal to occur. Now, also, anytime you see in that benzene region, if you see a splitting pattern that looks like this, in other words, they look very symmetrical. Okay, you have a doublet and a doublet. We generally refer to this as doublet of doublet. And what that tells you is that you have a benzene that is di-substituted. Di-substituted benzene. Di-substituted benzene, and also that they are para-substituted. The substitution is para. In other words, you have benzene with a substituent here, another one with a substituent here. So this hydrogen here, so that is what that is telling you. Anytime you see in the benzene region, just like here, you see a symmetrical doublet, 2 doublets, then you know you are dealing with a para-di-substituted benzene. Para-di-substituted benzene, okay? That is what that is telling you, okay? Of course, you could see here, we already told you, you have 2 hydrogen here and 2 hydrogen. And that those will be these 2 hydrogen here. Because this hydrogen and this hydrogen are equivalent. this hydrogen and this hydrogen are equivalent. And this one and this here, they split each other. That is why you see the doublet. You see two doublets. Okay, so far so good. Now, the other point that you need to note here, if you recall when we did our NMR spectroscopy, let me clear all of this here. Okay, let me take this out. Whenever you have an NMR spectrum, the first thing I want you to do, you want to write out the data in a tabular form. In a tabular format, okay? Okay, so let us do that here. We see a peak at 1.3. Okay, you see it's a triplet. It has 3 hydrogen. Okay, then you come here, you see a peak at about 3 point, let's call that 3.4. We say it's a singlet. And we say it is, oh, by the way, this is, yeah, we say it is 2 hydrogen. Keep in mind, these 2 hydrogen here, these 2 hydrogen here belong to this right here, okay? So we say it's 2 hydrogen. Then we say this here, this peak right here, we say it is a quartet. Of course, it is about 3.9, let's say 3.9. I will say it is a quartet. And the number of hydrogen, we say it is 2 hydrogen. Because these 2 hydrogen here, this here, belong to this signal right here. Okay, and then finally, in the benzene region, let us call this 6.7 or 6.8, where's 6.7? Okay, doublet of doublet. We call that doublet of doublet. And how many hydrogen? It's 4 hydrogen. Okay, anytime you see doublet of doublet, you know that you have a para-substituted benzene in which you have 2 substituent, one, they are both in the para position. Now, okay, so now we have the data in a tabular form. Let us now begin to put everything together. Let us now begin to put the pieces together. Okay, we've already told you we've already told you we have a para substitution, okay? So there is something here and something here. Now, the next bit of information you have to look at, take a look at this here. And take a look at this here. These two sets of information here, what do they tell you? You have a triplet, I'm sorry, but let me take that back. This here, not that one, not that one. And this here. You have a triplet and you have a quartet. What does that tell you? You have a triplet and you have a quartet. What does that tell you? You have a quartet and you have a triplet. What does that tell you? Ethyl. Ethyl, excellent. Ethyl. Now keep in mind, what is the formula that you have here? The formula that you need to work with is C8, H11, 1 nitrogen, and 1 oxygen. Okay? we've already said that we have a benzene, so therefore we only have 2 more carbons to go. Now you guys just told us we have an ethyl. Okay? We have an ethyl, fine. So now no more carbon. We've used up all of our carbon. About the nitrogen, keep in mind whatever is going to be attached now has to be here. About the nitrogen and the oxygen. Okay? We have a singlet. We have a singlet here. So far we've accounted for this peak. We've accounted for these 2 here. The only thing that we need to account for now is 2 hydrogen, singlet. So what would that be? 2 hydrogen singlet. We have a nitrogen here. 2 hydrogen singlet. What do you think that would be? NH2. Excellent. NH2. If we assume this is what we've put in together, all these pieces so far. Now, what is missing here? What is missing here? The oxygen is missing. And that will explain why this here is 3.9, because if there was no oxygen here, ordinarily this peak here, these 2 hydrogen here, okay, because this is your quartet, this would be about 2.5. But because oxygen must be there attached to here, okay, so let me take that off. So therefore, we must have this oxygen, CH2, and CH3. Okay? Now, if you now take a look at this, we have all of the pieces that we need. This meets the molecular formula requirement that they're giving us here. If you take a look at this here, that's the same molecular formula as this. Now let us now put all the pieces together. Okay? This here, these are the benzene peak at about 6.7, doublet, okay, or these 4 hydrogens here. These are the 2 hydrogen on the nitrogen. That would be the singlet. That would be the singlet at 3.4. That is a singlet. It is a singlet because these 2 hydrogen here, are attached to nitrogen, and they do not see any other hydrogen. So that is why they are singlet. And finally, the CH2 here, this CH2 here, that is your quartet. Because according to the M+1 rule, those 2 hydrogens are seeing 3 hydrogens. And that is why the multiplicity for this is a quartet. And finally, this here, the methyl group, which is at 1.3, it's a triplet. It is a triplet because these 3 methyl groups are only seeing 2. This hydrogen on this methyl group are seeing only 2 other hydrogens, and according to the M+1 rule, that is 2 + 1 equals to 3, and that is why they are now a triplet. So therefore, the structure of the unknown that we have been given is this here. Okay, so when you have a problem like this, you have to play a detective, or work like a detective and put all of the pieces together. And the pieces that you put together must be consistent with the data that you are given. Okay? So therefore, That is the structure of your known compound. Now, if you follow that, give me a happy face. Okay, excellent, excellent, excellent. Okay, I think we've gone 20 minutes past 9. I don't want us to waste too much time left. The last question, really, everybody should be able to do that. So I'm going to leave that last question to you guys to do. And what does it say? Using specific examples, write 5 methods for the synthesis of amine. Everybody should be able to do that. I will give you a few examples, for example. Okay? Okay, reduction of LAH, reduction of nitro group. That is one. Lithium aluminum hydride, followed by, that is one. Okay. Reduction of a nitride with LAH. Followed by hydronium ion. That is another method. So anyway, if you recall, during the class session, I gave you a whole series of methods for transforming for the synthesis of amine. So what I want you to do, go back to your notes and your text. You will see a whole series of reactions that will allow you to make amine. So if there is no question, we have come to the end of our session today. It's almost at 9:30. Is there any question before we leave today? Okay, I will stay around for another 5 minutes after I turn off the recorder. So if you want to ask me a question off the record, I will be around for another 5 minutes. Okay? Okay, if there is no question, I am going to turn off the recorder now. So you guys enjoy the rest of your evening. I will see you in class tomorrow.